The Coefficient of Restitution. Presentation by Connor Johnston. To understand what the coefficient of restitution is, we need to look at the ways different types of collisions work again. There are two types, elastic and inelastic collisions. If we assume no external forces act in our system during a collision, then momentum is conserved for both types. For an elastic collision, kinetic energy, which we know to be 1/2 mass times velocity squared, is also conserved in the system. It can be transferred between objects, or one object can bounce off something stationary with the same speed it had before. Momentum is still conserved for an inelastic collision, but at least some kinetic energy is lost to other types of energy like thermal. One example showing kinetic energy being lost is a small, fast object hitting a heavy object. Momentum is conserved, but due to the effect of the collision on the velocities, kinetic energy is not conserved. A perfectly inelastic collision is one in which the most possible kinetic energy is lost. In this kind of collision, the objects stick and stay together after the collision has ended. The coefficient of restitution, CR, is a way to gauge just how elastic or inelastic a collision is. The coefficient of restitution can also be denoted with the letter E. It relates the relative velocities of objects before and after a collision. A perfectly elastic collision will have a CR of 1, and a perfectly inelastic collision will have a CR of 0. To be specific, the coefficient of restitution is the ratio of the velocities of one object relative to a second object before and after it collides with said second object. Essentially, its relative velocity after the collision over its relative velocity before the collision. This is the definition in equation form, where u is initial velocity and v is final velocity. If this doesn't equal 1, the collision isn't perfectly elastic. This is derived from the momentum and kinetic energy equations of a perfectly elastic collision. CR derivation. The kinetic energy equation for a perfectly elastic collision is rearranged like so. The momentum equation is rearranged as well. Dividing the rearranged Ke by the rearranged momentum results in this. At the end, we find that the equation is the same as the one for CR shown earlier. An answer of less than 1, sure enough, indicates an inelastic collision due to the way that velocities are affected when kinetic energy is lost. This is a simplified version for when object 1 collides with a flat, stationary surface, which sets object 2's velocities to 0. The simplified version can be derived from the square root of the final kinetic energy over the initial kinetic energy. The halves and masses cancel out to equal the above equation. If the object is dropped from rest over a stationary surface, then the kinetic energies can be substituted for gravitational potential energies equal to the mass times the gravitational constant times the height. Big H is the drop height, and little h is the full height the object reaches after bouncing. Let's test our understanding with a pull question. A magnetic ball is slid on a frictionless surface, this means there is no rolling, with velocity v towards an unpowered electromagnet sitting at rest. Before the ball hits the electromagnet directly, the magnet is powered on, and the ball is quickly repelled away at a speed of 2v. The electromagnet is sent sliding away at a speed of v. Assuming no external forces, how should we expect CR to look for this situation? Now would be a good opportunity to pause. 3, 2, 1. The correct answer is that CR is going to be greater than 1. Collision occurs between the ball and the magnetic field generated by the electromagnet. We can use the CR equation for a two-object situation. It doesn't matter which direction is designated positive. It also doesn't matter which object is object 1 and which is object 2. Just stay consistent. I'll personally choose right as positive, and the ball as object 1. Velocities from the final condition go on top, and velocities from the initial conditions go on the bottom. We arrive at CR equals 3, making it a super elastic collision. CR equals 0 for perfectly inelastic collisions that lose the most possible kinetic energy. CR equals 1 for perfectly elastic collisions that keep all possible kinetic energy. It's possible for CR to be greater than 1 when energy is released during the collision. In the question, additional energy came from the magnetic field being turned on with the ball already within its range. Let's test our understanding further. The basketball team lost the championship game because the ball was bouncier than what they were used to. Before leaving, they have a player that's good at estimating forces dribble the ball. When the ball reaches its highest point, 1.17 meters, the player exerts a constant force over 10 centimeters on it towards the ground, and the ball doesn't rotate. The player believes that a range of 55 to 60 newtons of exerted force must have the ball return to its initial height after it bounces for it to feel like the championship ball. If every ball weighs 0.624 kilograms, find the range of CR values that work. CR values are for collisions between the balls and the standardized gym floors. This is a good opportunity to pause. 3, 2, 1. These 4 diagrams show 4 useful situations that the ball ends up in for finding a range of CR values. In diagram 1, it's beginning to be pushed towards the ground by the player from initial height. In diagrams 2 and 3, the ball undergoes a collision with the ground, which reverses the direction of its velocity and reduces its magnitude. In diagram 4, it's reached its max height again, which is the same as its initial height. First is diagrams 1 and 2. The work done on the ball by the player can be found with work is equal to force times distance. The peak gravitational potential energy of the ball all converts to kinetic energy as it falls. In the instant before the ball hits the ground, all energy from work done on the ball by the player and by gravity is turned into kinetic energy. This means that force times distance plus mass times g times height is equal to 1/2 the mass times the initial velocity squared. The initial velocity will be solved for. Next is diagrams 3 and 4. After bouncing, the ball will rise back up to initial height. All kinetic energy becomes gravitational potential energy again. There are no forces acting on the ball besides gravity. But the instant after the ball collides with the ground and has no height, it only has kinetic energy. This means that mass times g times the height is equal to 1/2 the mass times the final velocity squared. The final velocity will be solved for. Since the ball is exerted on by an outside force, the equation for CR for where an object is dropped from rest does not work. But since the ball is colliding with a stationary object, the simplified CR equation does work. CR can be solved with the prior found final and initial velocities. There will be 2 initial velocity values, one for the maximum and minimum exerted forces. Everything between those 2 CR values found will be our desired range. As stated before, we solve for the initial velocity. Then we solve for the final velocity. Then we divide the final velocity by the initial velocity. We plug values in and end up with 2 equations for CR, one where force is 55 newtons and one where force is 60 newtons. We solve for CR both times and find that the acceptable range is from 0.738 to 0.752. This looks within reasonability. Note that this smaller CR value came from when the force was bigger, and this bigger CR value came from when the force was smaller. Thank you for watching. I hope my presentation helped you. These are my sources.